Look at the sheer scale of a facility like this. To generate the enormous amount of electricity required to run a modern society, we have to build monumental power plants, often harnessing massive forces like a major river. But these colossal generation sites are almost always located hundreds of miles away from the dense cities that actually need the power. Delivering that energy isn't as straightforward as running a single long copper wire from the dam's generators straight into your living room. As electricity travels through those miles of conductive wire, the wire itself pushes back. This physical friction inside the metal is called electrical resistance. The physical environment acts as a natural barrier. The further you try to push the current across the map, the more the wire fights the flow, slowly draining the energy away. This chart plots heat loss against electrical current using the equation I²R. As you try to push more current through the wire, the energy lost to heat doesn't increase at a steady rate. It scales exponentially. If we attempted to pump the raw electrical current directly from the power plant across the country, the results would be catastrophic. The friction would generate so much heat that the transmission lines would literally melt and fail, or all the usable energy would simply burn off into the air long before reaching a single light bulb. To build a grid that spans a continent, engineers had to find a loophole. They needed a way to alter the properties of the electricity while it was in transit, dropping the current to survive the journey without losing the actual power. Total electrical power is calculated by multiplying voltage by current. Think of voltage like water pressure and current like the volume of water flowing. If we want to maintain the same total power, but reduce the dangerous heat-causing current, the math gives us exactly one option. We have to increase the voltage. The transformer occupies this role: two isolated wire coils wrapped around a shared iron frame. Alternating current flowing into the first coil creates a fluctuating magnetic field. This field travels through the core to the second coil, inducing a brand new electrical voltage inside. The outcome is determined by the turns ratio, the difference in how many times the wire is wrapped around each side. By wrapping more loops on the output side, voltage is stepped up and current is stepped down. Electricity enters as a high current hazard and leaves as a low current beam of energy. This geometry of coiled wire functions as a frictionless translator, allowing the power to bypass the physical limitations of the wire and cross the map. While the math is elegant, the physical machine is bound by the limits of the material world. Some of that magnetic energy escapes, creating eddy currents, rogue electricity swirling around inside the iron core itself. These stray currents, combined with the natural resistance of the copper wire, generate intense heat. Without management, the massive iron core and the windings would eventually reach self-destructive temperatures. To prevent a meltdown, the core is submerged in oil and uses massive cooling systems. These heavy radiator fins constantly draw the heat away. The operational lifespan of the grid's most important asset is defined by this continuous engineering battle against thermal overload. With the current lowered and the heat managed, the power can travel. Huge transformers at the generation plant step the voltage up to massive levels, sometimes 400,000 volts, so it can shoot efficiently across hundreds of miles of open country. When that high voltage power finally reaches a city, it enters a substation. Here, industrial-scale transformers catch the energy and step the voltage back down to a safer distribution level for urban routing. Finally, out on your street, the local transformers perform one last step down. They drop the electricity to a safe 240 volts just before it enters your home. These three carefully calculated intervals of stepping up and stepping down allow vastly different geographic spaces to function as a single, unified machine. This electromagnetic transition is the bridge between the raw, kinetic energy of a power plant and the delicate electronics of a modern home. That humming, heavy metal box out on the street isn't just a piece of infrastructure. It is the precise mathematical linchpin holding the modern world together.